Hey everyone, so welcome to the first lesson of the Global Climate Unit. And as was probably discussed in class, this unit will cover a whole host of issues related to climate change. But first, we have to get a foundation of how the atmospheric system works, and in order to understand why climate change is happening a little bit more. In terms of the Earth's atmosphere, the atmosphere is a mixture of solids, liquids, and gases that are held near to the Earth by gravitational force. So we have about 80 kilometers of atmospheric conditions that consist of mostly nitrogen, some oxygen, and other trace gases like carbon dioxide or helium or ozone, which help to block some of the solar radiation from coming in. There's also water vapor and other solids like dust and ash and soot that naturally exist, but can also be inflamed by other things like human activity. Now, most weather conditions occur in the lowest 16 to 17 kilometers, so about the lowest 10 miles of the atmosphere, so that closest to the surface of the Earth. This is called the troposphere. And temperatures decrease as the height increases. That's why if you go up to the mountains, it's colder than when you're closer to the surface of the Earth. And this is also due to water vapor being contained in the lowest 15 kilometers of the atmosphere. And so that's why we feel these conditions at this level. So here we can see the just a visual of it. You have the troposphere, which, like I said, 0 to 10 miles. That's where most weather patterns end up occurring. Above that, you have the tropopause, where the ozone layer is, which again blocks out some of that solar radiation from from coming in and from other radiation escaping. Above that, you have the stratosphere, which goes on for 20 miles above that, the mesosphere, and then you start to get into outer space, where you have the thermosphere and the exosphere. So at the tropopause, like I said, this is the boundary between that troposphere and the stratosphere. The temperature decline ceases. In the stratosphere, there's an increase in temperature, so things get a little bit warmer due to the presence of that ozone, which acts as a bit of an insulator in some ways. And then the temperatures fall again in the mesosphere, so that layer above the stratosphere, and then they rise again in the thermosphere. So things go from rising to falling to rising to falling as you go through the different layers of the atmosphere. So in terms of the atmospheric energy balance, like we've mentioned or hinted at, the atmosphere receives energy from both the sun and the earth. There's an open energy system that ends up taking place. The Earth's energy contribution is much smaller, but it has an important local effects like urban heat islands. And a lot of this comes from heat that's being released from the Earth as well. The energy, though, driving all weather systems and climates come from the sun. The Earth absorbs most of this energy, specifically around the equator in tropical regions, where there is a loss of energy from regions near the poles. And so in order to compensate and to make sure that as much of the Earth as livable as possible, the Earth also redistributes that energy from lower latitudes to higher latitudes, which are caused by wind circulation and ocean currents, bringing that warmer weather to these areas. So in terms of thinking about how this energy is spent, because we are getting a lot of radiation from the sun, there's something that sort of keeps the system in balance called an energy budget. And this is the balance between the amount of energy that gets to the Earth from the sun and the amount of energy that flows from the Earth back out to space. And a lot of this is regulated through a natural condition called the greenhouse effect. And so until recently, the atmosphere has been able to keep that energy within balance. The atmosphere is not getting necessarily hotter or not hotter in any sort of quick way that would throw off the balance that preserves life here on Earth. However, the balance between the inputs, so the incoming solar radiation from the sun, and the outputs, that radiation that is reflected from the Earth back out into space, is sort of being thrown off by a couple things. And this recent heating is known as global warming. And as you can see there, I've made sure that you can see it. And so this has been linked to human activities like land use changes, like we talked about in the urban environments unit, where we're, making things that absorb more, heat and keep things hotter here on Earth, but also the use of fossil fuels, which act as greenhouse gases that absorb greater amounts of heat. So under natural conditions, the balance of the energy budget would be achieved in three main ways. For one, you have an emission of electromagnetic waves and radiation that radiate at a temperature of about 5,700 degrees Celsius that come from the sun. But then you also have convection, the transfer of heat by the movement of a gas or liquid, and conduction, in which contact ends up being made at the surface of the Earth. And so all of these things help to keep the Earth in balance, but as we said, there's things that are throwing it out of balance, like human activity. Thinking about the Earth atmospheric energy budget, there's a breakdown of insolation that we have to talk about. Only about 46% of the incoming solar radiation from the sun, which is also known as insolation, at the top of the atmosphere actually gets through to the Earth's surface because it's been reflected back into space by the ozone layer. 31% of that insolation is reflected back into space, like I said. And then 19% is absorbed by atmospheric gases. So clouds end up doing a lot of the work as well, in which they reflect up to 80% of the total insolation back into the atmosphere. And so it doesn't necessarily come down to Earth. So the energy received from the sun by the Earth is then re-radiated at longer wavelengths. The sun emits at a short wavelength. So when you hear me talking about long wavelengths or short wavelengths, just know that the radiation coming from the sun is short. It hits the Earth. It becomes then long wave lengths from there. So 46% of that energy that finally gets to the surface is absorbed by the Earth's surface. 7% is lost into space. And then the clouds in the atmosphere also absorb some of that reflected long wave energy and re-radiate it back to Earth. Evaporation and condensation also play a role. They play a role of about a loss of heat of about 22%. And so all of these things work in concert here to sort of keep Earth's atmosphere in check. So one of the concepts that's going to be really important to us throughout this unit is this concept of albedo. And it's the ability of surfaces to reflect sunlight. So a couple of just like generalizations that we want to be thinking about here is that lighter colored surfaces have high albedo and as they reflect light more, right? And so that's why when we saw like the Phoenix Urban Heat Island video, they wanted to paint things white or have white roofs because the building did not absorb as much of that heat. It sort of just bounced off of it and things did not become like naturally much warmer because of that. Darker colored surfaces absorb radiation more, so low albedo. So ice and snow have a high albedo, meaning that they reflect light more and therefore, are slower to melt and things like that. However, once that melt does happen, you have darker surfaces underneath like grass or pavement that is going to absorb that heat more from there. And so as ice and snow is lost due to things like global warming, there's going to be a lower albedo surfaces that are going to absorb more of that heat. When thinking about incoming or shortwave radiation, I mentioned this a couple slides ago, but that incoming solar radiation, that shortwave radiation, is the main energy input into this atmospheric system that we're talking about. And it becomes affected by, which latitude you're living at. Again, if you're closer to the equator, you have more of that solar radiation coming in. If you're further away, you have less, but also the season that you're in, the cloud cover that exists, and this can even include the elevation at which those cloud levels are. So the higher the cloud or the less cloud cover there is, there's more radiation that is received by the surface of the Earth. So the other type of radiation is long-wave radiation, and this is the radiation of energy that has come from the sun originally but has now bounced from the Earth and back into the atmosphere, and for some of it, eventually back into space. So when we're thinking about long-wave radiation, during a cloudless night, there's a huge loss of long-wave radiation of the Earth, because due to the lack of clouds, that long-wave radiation that has existed in the atmosphere all day while the sun was shining has nothing to sort of bounce it back to the surface of the Earth. And so there's very little return of long-wave radiation from the atmosphere. And so because there's less radiation coming back down to Earth, you tend to have a cooler night because of that, because that radiation is gone, and that was representing that heat. However, on cloudy nights, some of that long-wave radiation is brought back down to the surface. And this reduces the overall loss of energy. And therefore, it makes it likely warmer. So hot desert areas, which do have a lack of cloud cover, have a huge loss of energy at night, because even though it's extremely hot during the day, the lack of clouds mean that radiation then escapes into higher elevations of the atmosphere that is not felt at the surface. And so there's a huge drastic change in temperature that is felt at that point. That gets us more fully into the greenhouse effect. So the greenhouse effect is the process by which these gases have been able to absorb some of this heat and to keep our Earth and our atmosphere warmer. And so these greenhouse gases allow shortwave radiation from the sun to pass through the atmosphere. However, they're able to trap that heat before it goes back into space. And unfortunately, this has been an increasing proportion that is throwing things out of balance. However, just in terms of how the greenhouse effect usually works, is that radiation trapped leads to a warming of the atmosphere. And so overall, life could not exist without the greenhouse effect, because it would be far too cold if we allowed all of the heat to go during the day. And it also helps to block out some of the radiation so that it doesn't become unnaturally hot where things are dying off. So for instance, the moon, as it says there, has no greenhouse effect, even though it's roughly the same distance from the sun as the Earth is. However, it goes up to 100 degrees Celsius during the day and negative 150 degrees Celsius at night. All right, at this point, you're going to go over to chapter 4b, and you're going to answer the rest of the questions. At this point, let me know if you have any questions, and have a great day.